Swayam Prabha. Digital India. Educated India.
Now, what I said is this scheduler is actually bring the help us to achieve sharing of the resources. So, remember the discussion, you have a router, you got a capacity, and then not necessarily one user, you might be receiving packets from so many network 1, 2, 3, and this is the network, this is a router which is inside the network number 4, and the exit link has got a finite capacity, and you want to receive packets from all these networks and then transmit on this link to the next hop. So, that is actually sharing of the resources. You want to optimize you want to transmit all of these packet received from all of these networks and send it to the next hop, respective next hop. Now, how does the scheduler actually work? So, let us formalize the discussion of the schedule, the previous diagram that you got. These might be users, end users, or other networks. So, even if it is other networks also, we call it as the users. So, I want to assign a kind of the allocation rate to each of these users, and the scheduler job is to assign that, to give that fair share of the share to all of these networks, all of these users and the networks. So, a link capacity, the outgoing link has a capacity C, and there are n users to serve, and each user has got the traffic from each user is identified by a flow. Fi is the ith users flows or ith network flows coming to a router in your network, and it is asking or transmitting at a certain rate called W of Fi. The ith user or ith network is transmitting at the rate of W of Fi right now, and I want to assign a priority to this transmission. I want to give a capacity of transmission. Assigning the priority means, now what we said is every 2 packets from the Q1, every 2 packets picked up from the Q1, 6 packets are selected from the Q2. So, if I want to do that, that is actually you are assigning a rate at which the user 2's traffic need to be transmitted. So, that selection or assignment of the weight is called as the RFI. It is called as the your transmission rate is, or the arrival rate is WFI, and out of that you are actually transmitting at a rate of RFI. This is called as allocation. So, user is transmitting at a certain rate, you are allocating something, that is called RFI. And what we want to do is the router to have the scheduler inside the router need to come up with some allocation scheme which is feasible. So, when this allocation scheme is feasible, when the rate of allocation or rate of transmission for all the users put together is less than or equal to the available capacity. What it means is, so summation of the RFIs, where I is varying from 1 to n users are there, and the capacity allocated to each of these user put together is less than or equal to the available capacity C. So, let us say the outgoing link is 1 Mbps, and the allocation scheme, the scheduler has come up with such a mechanism where each user's transmission rate is not or sum of the all the transmissions is not violating the constraint C. So, they are put together less than capacity of C, then only the allocation is said to be feasible. So, it is obvious that no user single user RFI, no single allocation is actually going the or exceeding the capacity C. If the sum of the allocations need to be are bounded by this capacity C, then the individual user transmission is also bounded by the capacity C. So, now the scheduler has to come up with this kind of the vision. So, now what we do is this schedule is feasible when this constraint is met, and I want to maximize or come up with such allocation scheme where without reducing the bandwidth of the particular user, I want to maximize the available utilization. So, I do not want to suppress another flow from the another user, my peer user, but I want to maximize my own transmission. My means the router is actually doing, it does not want to hurt me, at the same time it want to also utilize the available capacity, and I want to give a maximum amount of the bandwidth that is available to me at this point of time. So, that is where an algorithm called as the max min fair algorithm comes, and if this condition is violated, then the max min fair algorithm is actually said to be not feasible. So, let us see how exactly this max min fair scheduling algorithm exactly works. So, the way max min fair scheduling algorithm works is, it picks up that flow, every user is transmitting at a certain rate, and the flow, the jth flow which is having the transmission minimum transmission rate among the n users, you pick up that users first and then see what he is asking for. If Fj is asking for the fair share of the bandwidth, so C is the, look at this diagram. So, there is a router, there is the capacity of this n, there are n users 1 to up to n, and C by n is the fair share of the capacity available to one user, and if the rate at which the certain user, if user number 1 is transmitting at a capacity less than C by n, if let us say C is 1 Mbps and the users are 10, so 1 Mbps is divided among 10 users, and 1/10 of the Mbps, 0.1 Mbps, if the transmission rate of the user 1 is smaller than C by n, then you allocate whatever he is asking for, that you allocate to the user number 1, that is what it says. And on the other hand, if the transmission rate of the user is exceeding C by n, then you reduce it, ceiling of that allocation would be C by n. Whatever it is paid share, if it is transmission rate is less than that, then you give the full capacity to that user. If your transmission rate is exceeding the fair share, then you restrict it to the fair share. That is what is done here. If Wfj is greater than C by n, then they set the allocation scheme to R of Fj allocation is restricted to C by n. And then once you do the allocation, you update the number of the users that are transmitting and the capacity that is available. Once you do the one allocation, number of the users would be reduced to 9 and the capacity will be appropriately reduced by whatever the allocation you have done. So, that is how you do it, you iterate it, you take one user, ask what is he asking for, is he asking or transmitting or asking for something more than the fair share. If it is, restricted to fair share. If his transmission rate is less than or equal to his fair share, then you give him whatever he is asking for. That is what, maximize the transmission by serving the people who are asking for the minimum amount of the share. That is what the max min fair scheduling is. So, here is a picture which is actually showing 4 users, and the outgoing link, this capacity is 1 unit. 1 unit might be anything, might be Mbps or the Gbps, let us assume 1 Mbps, and these users are also asking for in Mbps. The user number 1, the flow number 1 is 0.1 Mbps, flow number 2 is 0.5 Mbps, flow number 3 is 10 Mbps, and flow number 4 is 5 Mbps, or you can call them as users, and those packets are arriving at the router R1, but the outgoing link capacity is only 1 Mbps. Now, how do I do the scheduling? How do I assign the weights to the different users traffic is the one. So, in the round R1, what you do is you pick up the user who is asking for the lowest quantum of the bandwidth. So, which is turns out to be the user 1, and he is asking for 0.1 Mbps. And what is the fair share now? There are 4 users, n is 4 and the capacity is 1, 1 by 4 is 0.25. So, the fair share of the user 1 is 0.25, but its peak transmission rate is 0.1, which is less than the 0.25. You allocate 0.1 Mbps to that user, whatever he is asking for, you just give them, and now you update. So, what you update? Now, after you do this allocation, the capacity would reduce to 0.9, 0.9 Mbps is available, and the number of users which are yet to be served is reduced to 3. That is what happens in the round 1. Now, in the round 2, the available capacity is 0.9 and there are 3 users, the fair share becomes 0.3. You look at what is the next user who is having the demand, lowest demand is the user number 2. He is asking for 0.5 Mbps, but the fair share turns out to be 0.3 Mbps. So, you give them R of F2 would be 0.3 Mbps, you update the capacity. Now, 0.6 is left and the number of the users who are yet to be served is 2, that should right. And in the round number 3, who is the user who is having the next lowest demand is the user number 4, and the available capacity is 0.6, user to be served is 2, and now the C by 2 is going to be 0.3 and he is asking for 5 Mbps, you give him 0.3 Mbps. And the last one which is having the highest demand is the user number 3. Now, again you update after the round 3, the available capacity is 0.3 and n is equal to 1. And now, in the next iteration, in the 4th iteration, so 0.3 is the leftover capacity, 1 user is left to be served. So, 0.3 is the bandwidth, 0.3 Mbps the bandwidth given to the user number 3. So, that is how you maximize the capacity allocation to the users who are having the less demand and curtail the transmission rate of the other users which are actually transmitting at a higher rate. That is what the max min fair scheduling is. So, this max min fair scheduling is bringing a notion of the fairness among the prioritized transmissions. So, again, if any of them, these users, when I say user 1 to 4 is transmitting now, that is an instantaneous transmission. If subsequently, if I do not have the transmission from the user number 4, then only among the 3 you adjust the transmission rate and then you do the transmission. That is how the maximum pair scheduling actually work. Now, this is one kind of the scheduler, and I want to end the discussion on the traffic management with another scheduling algorithm called the earliest deadline first scheduling algorithm. So, this earliest deadline first scheduling algorithm comes from the notion of end-to-end delay. So, particularly if you can recollect your earlier discussion that the audio traffic has to be delivered at the other end at a certain deadline. Source is here and the receiver R is here, and the packets are going through a bunch of intermediate routers, and it is reaching the receiver R, and the end-to-end delay is, let us say, 10 milliseconds, and the number of the routers in between is, let us say here in this case is 5, and at each router the maximum amount of the time that it can spend is turns out to be 2 milliseconds. Within 2 milliseconds these routers have to forward that particular packet. Now, what that is the constraint on the individual router, given that the number of the routers in between the source and receiver is 5, and the 10 millisecond is the total end-to-end delay time. Now, what I do is, when the packet arrives at the input queue of any router, I am going to assign a deadline for that packet to exit that router. So, within 2 milliseconds this packet has to exit. So, here is the if a packet Pij is the jth packet from the ith flow means ith user or ith network, whatever you want to call, from the ith user jth packet has come and it is carrying Lij amount of the bytes inside that, and that packet itself has arrived at the timestamp Aij. So, Aij is the timestamp. Let us say the timestamp now is 1 hour 0 minutes 32 seconds, and the 10 milliseconds 2 milliseconds is the deadline. So, I am going to set this the deadline for this packet 1 hour 0 minute 32 seconds comma 2 milliseconds. So, that is the time by which this packet P1 has to exit the network, exit the router and go to the next hop. So, that deadline timestamp is called as the Fij. Fij is the 1 hour 0 minutes 32 second, 2 millisecond is the Fij. How did we arrive at? So, the timestamp at which the packet has arrived plus whatever the deadline di is the ith router's timestamp, whatever the delay you can afford at each of the router, that is dij, and I add these two and then assign this number, and a schedule is feasible. I need to schedule this packet such that this packet Pij exits the router within that timeline, whatever the deadline that it is set. Fij is the deadline for the jth packet from the ith route, ith network or the ith user. So, that condition is met in that. So, I am going to transmit that packet which has got the earliest deadline, that is going to transmit it first. And it turns out that because the packets have got a variable amount of the data, and a router C is the capacity or the rate at which the bytes are transmitted from this router, and Lij has got a variable amount of the number of the bytes in it. Let us say the rate at which the packets are transmitted is the R byte, maybe 10 bytes per second, and the Lij has got the 100 bytes. So, the transmission time for this packet is going to take 10 seconds, and a necessary condition for the earliest deadline for scheduling to work is you have to meet this deadline. That can happen only when your Dij is smaller than Lij divided by the capacity rate at which the packet is actually transmitted. So, what it means is, if Lij is the, if packet Pij arrives with the condition that I need to exit this router number R1 within 2 milliseconds, and the amount of the data that is inside this packet is actually 100 bytes, and going by the rate at which the bytes are exiting or rate at which transmission is done, it is taking 10 milliseconds. The 2 milliseconds transmission deadline cannot be met. So, if that is the situation, then the scheduling itself we say that that is not feasible. A necessary condition to work for this kind of the scheduling to work is Di need to be the deadline at an individual router for any packet need to be smaller than the transmission time of that packet. They going by how many bytes are available in that packet and how much time it takes to transmit that packet. The deadline cannot be bigger than that, smaller than that. So, if it is the deadline is bigger than that, then you can always do the transmission. So, a necessary condition to work is Di need to be the transmission time need to be smaller than the deadline time. So, then only the scheduling can work. So, this turns out to be a necessary condition, but it is not a sufficient condition. Having said that, if every transmission takes less amount of the time than the deadline that the packet has got, then also the schedule earliest deadline for scheduling may not be feasible. So, I will leave it as an exercise to figure it out why this is not a sufficient condition.